So Gaussian singular integrals is a topic that has been in my career since my doctoral dissertation. And I want to report, finally, like a closure of certain topics there, right? So so first we will discuss the development of process of Gaussian singular integrals, which is the Gaussian Ritz transform, higher order Gaussian Ritz transform, and then discuss the LP properties and the Wickman one. Then we will consider the generalized Gaussian singular integrals and discuss the Pandanus property. And for reasons that will become clear later on, then there are other types of Ritz transform that I call it alternative Ritz transform. So we will discuss those ones and then discuss the properties. And finally, we will introduce a new class of Gaussian singular integrals that are what we call the generalized alternative Gaussian Ritz singular integrals, and then discuss the property. In particular, the generalized Gaussian singular integral is a large class that contains, as we are going to see, the Gaussian Ritz transform and the higher order Gaussian Ritz transform. And the generalized alternative Gaussian singular integral, as you will see, is not really a surprise. Will contain everything that is in the side of the alternative Ritz transform, higher order Ritz transform. So okay, so first of all, in the Gaussian world, we are working with the equivalent to the Laplacian is the Orsen-Uhlenbeck operator, which is half the Laplacian. Well, this is the normalization that we use, minus x times the gradient, right? And this operator, different from the Laplacian, has a discrete spectrum, and the spectrum of this operator are the Hermite polynomials in D variable, which is just the tensor product of one-dimensional Hermite polynomials. And then the link is that the Gaussian measure that I should have written there, the usual Gaussian measure, the Orsen-Uhlenbeck is self-adjoint in L2 of the Gaussian measure. So this is the symmetric Laplacian in this world. This operator can be decomposed using the usual derivative, well, properly normalized just to make things nice. And that is what in quantum mechanics is called the annihilator operator. But the problem is that when you try to do the integration by parts, it's clear that this guy is not, it's not symmetric nor antisymmetric in L2, right? Because when you take the derivative, you have to take derivative also of the exponential part, right? And therefore, the formal L2 adjoint is this guy. And that's just computation by integration by parts, right? And that's what is called in quantum mechanics the creator operator. And then this can be written in a more nicer form in Rn using this form. Okay, then the Orsen-Uhlenbeck operator can be written as the sum in each variable of the derivative, the annihilator operators apply composed with the creator operator. And the problem of this, as we are going to see, is precisely that in this case, these are not commutative. I mean, if I reverse the order, I will not get L. That's one of the important observations here. Okay, so the Gaussian Ries transform, well, there are several ways to define them. This is probably the most straightforward. You take the minus the Orsten-Uhlenbeck, take the inverse of the square root, and take the derivative of it, the Gaussian derivative, right? The one that we just considered, this guy. So that's, I mean, morally speaking, similar to the classical case what we do. Of course, in the classical case, you can check that using Fourier transform. Here, the analog is looking at the action over the Hermite polynomial, and this is the action over the Hermite polynomial. Okay, so it can be proved that the kernel of this operator is this guy, and this is coming from a representation of this guy that is, well, one of the Ries potentials, but I don't have the time to go into those details, but you should believe me, you can get this guy. This is the kernel, and therefore the Ries can be represented with this integral. See that this guy is not a convolution operator because we have this R here that bother us. Okay, so in 1969, with another motivation, Benjamin Mackenhop discussed the one-dimensional case, the Gaussian Hilbert transform. He used, you know, the more classical approach of the conjugation and the equivalent to the Cauchy-Riemann equations. And he proved with very hard computations that this guy was bounded from LP to LP. From another point of view, Paul-André Meyer have considered in Rn, in Rd, he proved the continuity of the Ries transforms using probabilistic methods, using Brownian motion, Burkholder-Ganda inequality, very heavy stuff in probability. And the constant, since it's a probabilistic method, the constant was independent of dimension. Right? Well, several proofs of this have been done. Richard Gandhi also considered a very nice proof, a probabilistic topic, method using Brownian motion and the notion of what he called the background radiation. And then in 1988, Gilles Pissier got something which is in between probability and harmonic analysis, because he used a method of rotations and transference method. Right? And again, all of this method, the constants are independent of dimension. In my doctoral dissertation, oh, what is this? What is happening here? I don't know what is going on, sorry. Oh my goodness. So, sorry. It got crazy. Okay, sorry. So in my doctoral dissertation, I got the first proof using purely analytic method, what you can call kernel method, for d bigger than 1 by studying the kernel, this guy, in detail, right? And so I proved that extending the Markov proof in higher dimension, but the constant, unfortunately, depends strongly on dimension. And then Christian Gutierrez got an alternative proof using the Littlewood-Paley-Stein theory with constant independent of dimension. And finally, for the Riesz transform, we have in 1996 a beautiful and powerful work by Sonsoles Perez and Fernando Soria that got an alternative real analysis method proof using refined estimate of the kernel. They first proved that the maximal function of the Ornstein-Uhlenbeck semigroup, and using the same method, what they were able to cover the singular integral. Then Markov already have for the Hilbert transform the weak 1-1 type. And in 1993, Roberto Scotto got the proof in the weak type 1-1 for the Riesz transform. Also, Sonsoles got an alternative proof of this result. So this is Gaussian Riesz transform. Higher order Gaussian Riesz transform, well, in the Gaussian case, it's kind of simpler than in the classical case. You just change the order of differentiation and you have to go higher in the order of the Riesz potentials, right? And then since you have that they are going to be also, the Hermite polynomials are eigenfunctions, you get this explicit expression for the higher order Riesz transform. Okay, then, yes, guess what? Chance to the representation of the Riesz potential, you can get this kernel for beta. When beta is equal to 1, you are back to the Riesz transform. Okay. And the interesting thing here is that here appears, because when you are taking derivative with respect to x, you are taking derivative of the exponential, and here appears the Hermite polynomial. So that was something that we realized early in our work, that this term here was nothing but the Hermite polynomial evaluated in this guy, in the J variable, right? Okay, so here this is what we have, the Hermite polynomial of order beta, where beta is precisely the order in which you are taking the derivative, right? Okay, so I also, in my doctoral dissertation, gave the first analytic proof for that. And yes, the constants are depending on dimension. And then in 1988, also PCA have given a proof, but only for with constant independent of dimension, because they were a combination of analytic and probabilistic method. But his method only worked for models of beta odd. So I was able to publish my dissertation as a paper, otherwise I would be excluded, right? And then after the paper of Gutierrez, then Gutierrez, Segovia, and Torrea obtained with constant independent of dimension, following the work of Gutierrez, using Littlewood-Paley theory. Okay. Perez and Soria gave another analytic proof, depending on dimension, on similar techniques, the one that were developed by the Ornstein-Uhlenbeck maximal function. Finally, we got a very short proof, right? It's like a page and a half, Liliana Forzani, Roberto Scotto, and myself, using with constant independent on dimension based on Meyer's multiplication theory. But when you go to all of that, of course, for p bigger than 1, when you go to weak 1-1, we have a surprise. Roberto and Liliana in 1998 realized that in 1 dimension, the Riesz transforms of order 2 are weak 1-1, but any other one with order bigger or equal than 3 are not. That was extended for higher dimensions by Garcia Cuerva, Maucheri, Shulgren, and Torrea. Right? And Sonsoles also was able, using her method, very refined estimate of the kernel, that it was that yes, the order 2 is LP bound, is weak 1-1, but she gave alternative estimate for the case P1, but I don't have the time. I'm running out of time already. So in my dissertation also, since the beginning, you are trying to look for something that will be the equivalent in the Gaussian world of the Calderon-Zygmunt singular integral, a whole family of singular integrals. I gave a first formulation based on the on function that will not work, that will not grow faster than polynomials. But then Sonsoles got a much nicer characterization, that is any function such that has this orthogonality condition, has integral 1 with respect to the Gaussian measure, and this growth that cannot grow, the function and the gradient cannot go faster than e to the epsilon x squared. She was able to, so this is exactly the same as the higher order Riesz transform. The only thing is that we are changing the Hermite polynomials for f. And then, yes, you can get with this kernel, you can prove that this is a very elaborate argument that is not, I don't have the time. So, so in my case, initially I consider f and delta a gradient of f of polynomial growth. Of course, Riesz transforms are the case, as I already said, that f is just the Hermite polynomial of order beta. And she proved the LP, and she also proved that on certain condition on f, TFM is not weak type. And then Dalmaso and Scotto were able to extend this result to LP variable for LP Gaussian LP Lebesgue variable. Of course, the proof of all these results, well, the kernel proof are based on the fact that what is nowadays called the local part and the global part. The local part is near 0, and there you can control the Gaussian measure. So it's basically a multiple of the Lebesgue measure, and then there the local part corresponds to a classical Calderon-Zygmunt operator. And the rest, when you are away basically to the origin, is a positive operator that most of the time give you a lot of work to be able to estimate. Well, and here is the twist. As I said, if you change the order of these operators, remember in the Orsten-Uhlenbeck was this guy first and then this guy first and then this guy, you get the Orsten-Uhlenbeck. Well, when you reverse that, you get this guy, which is not of much interest in quantum mechanics precisely because it depends on D. We call that guy the alternative Orsten-Uhlenbeck operator, and yes, it's going to be also a discrete spectrum, and the Hermite polynomials are eigenfunctions. So this was something that Hugo, Aymar, Liliana, and Roberto realized that, well, if instead of of the Orsen-Uhlenbeck. You take the alternative Orsen-Uhlenbeck minus 1/2 and take not the usual derivative, but the other one, you can define other Riesz transform that I call it alternative Riesz transform. And then, of course, you can go for the same idea. You can go to any order, taking the adjoint of the beta derivative and taking the Riesz potential of the corresponding order, modulus of beta divided by 2. And this is the action, and there is a kernel for that. So they prove, it's a paper in Transaction, they prove that, well, we prove actually is using Paul-André Meyer multiplier theorem, we can prove this, that is LP bounded, and they prove that, and this is an interesting result, that no matter which order you take, these guys behave well. These are weak 1-1 regardless of the order, in different from the case. So I'm running out of time. So well, the new class that so this is another branch of Riesz transform. So the new class that we are introducing is taking the same F that took Sonsoles, right? We define using this the same idea, replacing this guy by F, right? We get the alternative Gaussian singular, generalized alternative Gaussian singular integrals. And well, it works. It took a while to make it work, but it works. Yes, you can prove, we prove that it's always LP bounded and it's weak 1-1 too. And then we also using the same conditions of regularity that Dalmaso and Scott got a regularity condition over the P that is necessary for the Gaussian measure to make it work. And following that, we also proved that these singular integrals are LP variable bounded. Additionally, a student of mine in Venezuela, in spite of all the situation, he did his doctoral dissertation on the study of the semigroup, which is bounded, LP bounded, variable LP bounded, but it is not clear whether they are constructions as in the original case. Okay, sorry, I think I went a little bit over time. So these are the reference, and that's it. So thank you for your attention. And if you want to learn more about Gaussian harmonic analysis, there is a book for that.